I would then get demonstrated. So hello, welcome everyone to another biomedical engineering seminar. I start with acknowledgement of country. I begin with paying my respect to the First Nation custodian of country throughout New South Wales, in particular the Gadigal people of Eora Nation, the traditional owners of the land on which the University of Sydney is built. I pay my respect to their elders, past, present, and emerging. I welcome you all again to this biomedical engineering seminar by Dr. Mahsa Shoaran. It's early morning in Switzerland, and she has been very generous accepting our invitation. Mahsa is from EPFL, and the talk today is on smart neural interfaces for chronic brain disorders. Dr. Shoaran was an assistant professor at Cornell and a postdoc at Caltech. And I think just a few weeks perhaps before COVID hit last year, joined EPFL as an assistant professor and a winner of Swiss NSF postdoctoral fellowship. She was also named as a rising star in electrical engineering and computer science by MIT in 2015. So today's talk is, as I said, on the cross-section between the circuit design, neural prostheses, and machine learning. And I'm sure we're going to learn a lot. So I'm handing over to you, Mahsa.
Thanks a lot, Omid. Thank you for the kind introduction, and also thanks for inviting me. It is really a pleasure to be with you today. I really wish that we could do this in person and I could, visit beautiful Sydney, but unfortunately that's not possible. So maybe another time in the future. So as Omid kindly mentioned, I am currently an assistant professor at EPFL, and we are part of the EPFL Center for Neuroprosthetics at Biotech campus in Geneva, which you see on the left. So my main lab is based in Geneva, and I'm also affiliated with the Electrical Engineering Institute of EPFL, which is in the main campus in Lausanne, which probably you're more familiar with. So I have a small lab also in Lausanne. So today I will present some of our recent work on designing smart neural interfaces, particularly by combining AI with neurotechnology for treating chronic brain disorders. So in my group, we are broadly interested in circuit and system design for neural interfaces. And to design more intelligent and efficient systems, we essentially combine integrated circuits with algorithms, particularly with machine learning. And we work in close collaboration with domain experts, meaning with physicians and neuroscientists. And research at the intersection of these domains allows one to tackle really interesting problems and really go beyond existing devices. So you could think of designing new technologies that could one day treat disorders such as epilepsy or Parkinson's disease movement disorders, which have been more commonly studied in the field, and even mental disorders such as depression or anxiety, dementia, traumatic brain injury, and many other treatment-resistant conditions, and potentially benefit millions of patients who are affected with chronic brain disorders. So a lot of exciting research is currently going on in this domain, and today I will briefly touch upon some of these applications and the work that we have been doing in my lab in this direction. So these neural interfaces essentially perform three fundamental functions. They record neural activity, process it in real time, and then deliver a therapy, which is typically in the form of electrical stimulation. And the goal is to diagnose and treat brain disorders. So the neural activity is typically, is recorded by different types of electrodes with different spatial and temporal resolution. For example, spikes or local field potentials are recorded by penetrating a deep brain electrodes, or for example, electrocorticography, which could be, we can record from the surface of the cortex. And there are also non-invasive ways to do this, such as EEG. But in my lab, we mostly use invasive techniques. So we design devices that are more compatible with invasive technologies. And then we basically design these tiny neural interfaces or microchips. So you can see these are tiny devices that perform these fundamental functions. And the challenge is basically to achieve the many requirements that we have on designing these devices, especially as we scale up the number of recording and stimulation channels. So we want these devices, for example, to be extremely low power, small, so that the surgery would be minimally invasive, low noise, and at the same time, we want to have high number of channels and also a wireless device. So achieving all these goals is something that makes the circuit design for neural interfaces quite challenging. So if we look at the recent trends in neural interfaces, particularly in the neural recording IC domain, we can see that there has been an increasing interest recently in designing high density systems. So maybe in the first decade of research in this domain, there was a lot of interest in designing ultra low noise and low power amplifiers, neural amplifiers. But more recently, IC designers have realized that it is also quite important to reduce the area, because the area is limited in these systems as we want to scale up the number of channels. So there's a lot of effort in, for example, reducing the size of the ASIC that is processing the signals that are recorded along, for example, this neuropixel shank. Or so there has been some recent work that is trying to completely basically integrate the recording circuitry along with the electrodes on the shank. But as you can see here, even though the area is quite compact, but the power consumption of this design is pretty high. So this is so there's a lot of challenge in achieving these goals at the same time. And the work shown here is basically implementing a multiplexing technique. So it's using analog multiplexing at the input to basically reduce the area, and is achieving a reasonable power and area per channel. And there are a few other designs like this. So when achieving this low power, low area goals, there are also other concerns in terms of, so we want to achieve a high input impedance, cancel the DC offset at the input, cancel stimulation artifacts as a result of stimulation in the same region as recording, which requires high dynamic range amplifiers. And all of this makes designing the neural interfaces quite challenging. But on the other hand, if we look at commercially available devices for brain disorders, we can see that basically they only, first of all, they only address a few neurological disorders, mainly Parkinson's disease and epilepsy. So there has been also some progress in building closed loop devices like the RNS device for controlling seizures, the responsive neurostimulator by NeuroPace, and also the Medtronic's Percept device, which combines deep brain stimulation with sensing. But all these devices have very few channels, so they basically have 4 channels and very limited embedded processing, which limits the accuracy of symptom detection in a closed loop system. And also there has been a lot of research on brain-machine interfaces and motor prosthetics, but as we know, today still we don't have any clinically viable BMI, but of course there's a lot of research going on in academia, and also in some neurotech companies are working in this direction. So there's basically much more that can be done from both circuit and algorithmic perspectives, either to improve the efficacy of current devices or to develop new devices for other indications, such as, for example, psychiatric disorders or memory disorders that are currently less explored. And on the other hand, there has been also many many advances in designing in terms of electrode fabrication, especially in designing high density sensing arrays. So for example, you see the NeuroPixel with thousands of channels, the high density ECOG array, or for example, the Neuralink threads with more than 3,000 channels. And there's even a Moore's law for neuroscience that actually predicts that the number of simultaneously recorded neurons actually doubles approximately every 7.4 years. And a lot of progress also in designing, for example, flexible implants using soft materials that could better integrate with neurons. But when we look at the options that are available in terms of therapy for patients today, there are actually very few devices, and they're not quite compatible with such advanced technologies. So we believe that this gap can be partially filled by designing better electronics that can reliably record and process and possibly even stimulate on many channels on a tiny and low power device with minimal surgical overhead. And many of us, and again, some neurotech companies are currently working toward this goal. So here I summarize some of the major goals of the next generation neural interfaces. And in my lab, we are particularly interested in the first three topics. So in designing high density and miniaturized systems that can also activate a therapy, particularly using machine learning based control strategies by integrating intelligence on the chip for closed loop systems. And there are many other groups that are also working on, for example, wireless power and data transfer, which are also extremely important for next generation neural interfaces. So this high density recording is so the recording of neural activity with high spatial and temporal resolution is essential for next generation neural implants for different applications. But the problem is that from IC design perspective, the problem is that simultaneous recording from many electrodes could significantly increase the data rate and power that is consumed by for transmission, which could be actually the bottleneck of the system in terms of power dissipation. So we previously implemented a method based on compressive sensing, as I'm showing here, to deal with this issue by basically applying a sub-Nyquist sampling of neural signals that are sparse in a given domain. So here we basically introduced a novel approach based on, so we implemented a mixed signal multi-channel compressive sensing system, which allows us to achieve up to 16 times compression with sufficient recovery of original neural signals, and this translates to the same order of increase in terms of channel density. So I will not dive into detail of the circuits, but just telling you that this is very efficient in terms of hardware implementation, because we basically encode the entire entire array, our multi-channel neural input, into a single compressed data stream with a single compression stage that requires only a single analog to digital converter. And basically, this results in a significant area and power saving. So the power and the additional power and area for compression circuitry is sub-microwatt per channel and a very small area, which is much better than other conventional compression methods. So compressed sensing is quite efficient for high channel count neural recording, especially when we want to stream the data for example, offline analysis, external processing of data. But the problem with compressive sensing is that it typically requires a complex reconstruction phase, which could be a bottleneck for real-time applications, such as responsive stimulation. So to avoid that, we took a step further and actually built a closed-loop therapeutic device, in this case, a seizure control system for epilepsy. So for 1/3 of patients with epilepsy who are medication resistant, neuromodulation is one of the few therapeutic options that is available. And the FDA-approved RNS device, which is basically a cranial implant, as you can see here, it So it has been more effective in clinical trials compared to open loop, for example, vagus nerve stimulator. But the problem with RNS, as you can see here, is that it is a bulky device. So a large craniotomy is required to implant this device in the brain, which could result in a high-risk surgery. And also it has very few channels, so basically 4 channels for neural recording, which significantly limits the seizure detection accuracy. So for this reason, RNS is known to have many false positives in continuous operation. So these drawbacks motivate us to design small, low power, and also more accurate seizure detection systems with higher number of channels. So there are many studies that show the seizure detection accuracy could benefit from higher density of electrodes. So to improve the hardware efficiency for seizure detection, we propose a new approach by implementing the seizure detection in the compressed domain. So we basically use our multi-channel compression that I just presented as a linear spatial filter. And we basically, as you can see here, we implement the seizure detection unit in the compressed domain. So we extract several time domain features, as you can see here, from the compressed signal to detect the seizure onset. So the total area of this system, including the recording, seizure detection, and the stimulation circuitry, was 1 millimeter square, roughly 1 millimeter square, which, and the sub-microwatt per channel was achieved for this system, which improved the state-of-the-art seizure detection systems by more than 40 times in terms of power area product per channel. So this is important if, so in cases that we want to use high channel count seizure detection in order to improve the accuracy. But one challenge again here is that similar to RNS system that performs this thresholding of single biomarkers for detecting the seizure, this approach that we simply threshold the biomarker for detecting the seizure onset has a limited accuracy in terms of seizure detection. So, and the reason is that we cannot effectively combine multiple features. So to address this issue, the recent approach that we are basically pursuing is to integrate a classifier directly on the implant. So the idea here is that we have an on-chip classifier and also biomarker extraction circuitry on the chip that detect the onset of symptoms for a disease in real time, and then trigger a neurostimulator to suppress the symptom. And this data-driven learning approach is important to detect patient-specific patterns in neural data in order to enable more accurate symptom detection and therapeutic intervention compared to, for example, conventional thresholding approach. So yeah, and basically machine learning is particularly useful in this closed loop system or closed loop bidirectional implants. So for example, the applications could be detecting and controlling seizures in epilepsy, as you can see here, or for example, tremor in Parkinson's disease, or change of mood in patients with mental disorders. And the recording and the simulation, so this can be in the same region, or you could record from one region and simulate in another region of the brain. And the application space for this basically smart neural interfaces is quite broad, and it is rapidly growing. So it's basically ranging from, so both in the neural interface IC domain and in clinical neuroscience, the applications are increasing, ranging from brain implants to, for example, spinal cord and peripheral interfaces. And another application for this on-chip machine learning is for motor decoding in brain-machine interfaces to perform, for example, decoding, as I showed here, finger movement classification or continuous trajectory decoding in order to activate the spinal cord stimulator, or for example, to control a prosthetic device or a cortical stimulator as a sensory feedback. So this is also an active area of research, designing brain-machine interfaces with on-chip decoding capability, which we are also very interested in this direction, but I will not be able to cover that today. And so what are the advantages of doing this or integrating machine learning on a neural interface? So it has several advantages over traditional interfaces that only transmit the raw data for external processing. So this local processing basically allows us to trigger stimulation with minimal latency. And this is something in the order of milliseconds compared to wireless systems that have hundreds of millisecond loop latency for closing the loop. And this is also based on accurate patient-specific symptom detection, which improves the efficacy of therapy and also reduces the side effects. And another important aspect is that by avoiding data transmission, we can reduce the power consumption, which is also a big challenge for high channel count systems. And also by doing this, we can improve the security and privacy aspects, which is also an important issue for medical devices. But despite all these benefits, deploying machine learning on a neural implant is quite challenging because of the extreme constraints for these implants in terms of power consumption and size of the implant. So basically we could consider an implant, I'm sorry.
That's all right. You can take your time.
I have had a cold the past few days. And the other challenge is that these classifiers need to process many channels, and that is something that is quite challenging when implementing an on-chip classifier. So if you look at the literature in terms of neural interfaces that have integrated classifiers on the chip, so the application that has been most popular is seizure detection for epilepsy. So we see devices that have, for example, on chip. So here we see a nonlinear SVM, which integrates an 8-channel EEG processor for seizure detection. And then more recently, we see more advanced systems based on decision trees that are more energy efficient for resource constrained platforms such as implantable devices. So if you look at tree-based models, basically a single decision tree is quite simple, but when we combine multiples of these trees, the resulting model could even achieve state-of-the-art performance. So here you can see a tree ensemble for 32-channel intracranial EEG-based seizure detection, which I'll get back to this in a minute. And later, there was another tree-based classifier, which again for seizure detection, which implements a large number of decision stumps, which are trees of depth 1 for 8-channel IEG detection. All right, so now I will talk about decision tree-based classifiers and the approach that we propose in order to efficiently integrate them on a neural interface. And after that, I'll present a couple other applications of machine learning for brain implants. So in this work that I'm showing here, jointly with mixed group at Caltech, we opted to implement an ensemble of gradient boosted decision trees for on-chip seizure detection. So the idea of boosting is basically to combine multiple weak learners in order to generate an accurate model. So to generate an accurate predictor, we basically combine a number of weak learners, which in this case is a decision tree in order to minimize the loss function on a training data set. And the choice of the model here, so basically the loss here is minimized by adding this decision tree is using a gradient descent procedure. So our choice of model was motivated by the high accuracy of this classifier in our own study and also in machine learning competitions on seizure detection in recent years, which this classifier was consistently one of the top performing models. And also what's particularly interesting about tree-based models is that they can be highly energy and area efficient, which makes them good candidates for implantable devices. So the reason is that these trees are quite simple. So we are comparing a feature with a threshold in each node. And also the other reason is that basically trees are compatible with a single path inference scheme. So this basically means that we can visit only a small portion of the model along a decision path to make a decision. Which, as you can imagine, this is much simpler compared to, for example, models such as SVM, which typically require a large number of multiplications and additions, and also the hardware complexity of SVM scales with the number of channels and input features. So for this reason, trees are more suitable for high density implants. And this is the hardware architecture that we implemented. So we use the single path feature extraction approach, meaning that we basically, each tree in the ensemble has only one feature extraction unit, which sequentially extracts the features so that it can support a large number of channels without significant increase in hardware overhead. And this is our feature set. So given the limited amount of data in these applications, we basically rely on handcrafted features. And we verified this on intracranial EEG data from 26 patients with epilepsy, which is provided by the Penn and Mayo Clinic open source IEG portal. In comparison, if we look at the performance of our implemented machine learning system on chip, this design achieved a significant improvement in terms of energy efficiency in a very small area per channel. And it could also easily scale to a higher number of channels without significant increase in complexity. So this particular design was for 32 channel IEG classification. And it also offers a scalability in terms of energy versus performance, meaning that we can activate only the required number of trees for a certain accuracy. So basically we can reduce the energy if we can achieve the same level of performance with a lower number of trees. So this was for seizure detection application, which, as I mentioned, has been very popular in the machine learning studies in neural interfaces. And now I'd like to talk about another exciting application of machine learning that we have so we have been recently working on, which is for Parkinson's disease, which is a prevalent movement disorder. So as we know, deep brain stimulation is commonly used to alleviate the motor symptoms of Parkinson and other movement disorders in the form of a constant high frequency stimulation of deep brain structures. And it has obviously clear benefits for the patients, but it also has side effects such as speech and gait impairments, mood changes. So depression is one of the important side effects, in addition to high energy consumption of the device and the need for battery replacement. And in addition, this open loop DBS is based on a predefined scheme for stimulation, which is regardless of the ongoing neuronal activity. So the idea of closed loop, or so-called adaptive deep brain stimulation, is basically trying to overcome these limitations by real-time activation and adjustment of stimulation based on feedback from a patient's clinical state. So this is currently a very active area of research, and a number of feasibility studies, which are pioneered by Peter Brown's group from University of Oxford, have shown that adaptive DBS actually results in motor improvement and also energy reduction and less speech impairment compared to continuous DBS, meaning that this is a more efficient and effective method for stimulation. But most studies so far have been using a simple thresholding of beta power extracted from local field potentials through the DBS lead for turning the DBS on and off, assuming that this is the key biomarker for Parkinson. But still the choice of the input signal, meaning whether it should be LFP or, for example, ECOG, the choice of biomarker and also the control algorithm is a challenge, and there are studies going on to optimize them. So considering that accurate and also reliable detection of tremor onset in Parkinson is critical to the efficacy of closed loop or adaptive DBS therapy, in a collaboration with Peter Brown's lab, we actually proposed a machine learning framework for tremor detection during rest state. So basically, we use a supervised learning algorithm to classify the local field potential recordings from the DBS lead. And we use the measurements from an accelerometer to label the data for the supervised learning. So basically, we use the data from 12 patients with Parkinson's who were implanted with DBS, and 3 bipolar channels in each patient were used for this study. So here you can see the example of LFP signal and the accelerometer that's shown here, and their time frequency decomposition. So what we did is that we studied the predictive accuracy of different biomarkers of tremor in LFP. So here you can see a list of features that have been studied in Parkinson literature. So these features include, for example, band power features, including beta power that is most commonly used, features such as phase amplitude coupling, and also some time domain features, which actually turned out to be quite important. So we applied the Kalman filter in the feature space in order to reduce the noise in the LFP and to basically reduce the number of false positives. With this feature set, we tested different classifiers for tremor detection. And we observed that by optimal selection of less than 5 features from our feature set, and using gradient boosting tree as our top model, we could achieve a pretty high F1 score and a high sensitivity, about 90%, and a detection lead of half a second, meaning that we can actually predict or anticipate the tremor state. And this is quite important because for closed-loop stimulation, we want to be as fast as possible in terms of delivering the therapy. So here you can see the classification result from the LFP signal on the top, which, as you can see, the tremor is detected at the output of the classifier. And to compare this with prior work, we also applied the threshold, the median threshold to beta power, which is the baseline approach. But the performance significantly dropped, which basically shows the advantage of a machine learning method for accurate tremor prediction. So this can be used to apply stimulation in a closed loop to improve the efficacy and also to reduce the side effects and energy consumption of open loop deep brain stimulation. But one challenge with this ensemble approach is that basically more difficult classification tasks may require a large number of trees to achieve a reasonable performance. For example, in tremor detection task or in motor decoding, which are more complicated than seizure detection, we needed a higher number of trees in the order of 30 or 50, which could increase the hardware complexity of our classifier and also the size of the model on the chip. So to address this, we recently proposed an approach based on oblique decision trees, as you can see here, which involves multiple features in the internal nodes in order to make a decision, as opposed to conventional axis-aligned decision trees, which only have a single feature in each node. So as a result, these oblique trees can generate accurate predictions even with a single tree. So here we use an oblique tree with a probabilistic routing, and from this we could derive the objective function and train the model with gradient-based optimization. So I'll skip the details of the training algorithm in the interest of time, but this oblique tree is basically, so the oblique boundaries that we have with oblique trees also known to better deal with correlated features, which is the case in neural signals. And in addition, another advantage is that in an oblique tree, the decision functions in the internal nodes is basically a logistic regression. This means that we can use methods such as weight pruning or weight sharing that are used in neural networks to compress the model. We can use those models in our oblique tree in order to compress the tree and create sparse connections. So this is the work that was done primarily by my PhD student Binjiao Zhu. So we basically introduced several methods to improve the energy efficiency of this model, which we call it resource efficient oblique tree, or RESOT. So one technique is what we call it energy aware learning, meaning that we can actually include the feature cost, for instance, power consumption, as a regularization term in the objective function of our model, and we apply this to our oblique tree. So here you can see in this table, so we have the normalized power consumption for different features that we used for tremor detection in Parkinson, which based on the previous study that I presented. So using this technique, we could actually design a model that tends to use a higher number of low complexity features, like this time domain features, compared to more complex, for example, band power features that consume a lot of power. And this work was funded by Google. And another technique that we applied was model compression. So by applying weight pruning and sharing techniques, we could compress the model and create a sparse oblique tree. So here the model size was basically, we were able to compress it by a factor of more than 20 with only a marginal loss in performance. And when we combine that by single path inference, as you can see here, we can basically, we only use a small portion of parameters during inference, which further improves the hardware efficiency. So this study was done on MNIST data set to compare with state-of-the-art models. And we tested this result, combining these energy efficient techniques on 3 neural applications, including seizure and tremor detection and finger movement classification using ECOG signal. So as you can see here, so in comparison to, for example, the conventional gradient boosting trees, which previously we showed that achieves a state-of-the-art performance in this task, or for example, power efficient gradient boosting trees, where we apply the energy aware learning to gradient boosting, result actually could improve in terms of both model size and power consumption. So these are the savings that you see compared to conventional gradient boosting models. So this means that we can use this approach as a low power and memory efficient solution for integrating a classifier on the implant. So the last topic that I want to briefly discuss is neural prostheses for mental disorders. So as we know, mental health disorders affect millions of people around the world. So in the US alone in 2017, 90% of adults experienced a mental illness. So depression is the leading cause of disability worldwide. And the prevalence of these mental disorders has been continuously increasing, and it is, of course, a major economic burden as well. And unfortunately, the statistics last year were also a lot worse. So CDC reported a significant increase in mental health conditions due to COVID-19, such as anxiety, stress, and depression, which also lead to increased suicidal or, for example, addictive behaviors. So we need to do much more in order to treat mental health disorders more effectively in the future. So in terms of therapies, open loop or continuous deep brain stimulation has shown some promising effects for treatment-resistant depression patients and also patients with OCD. So as you can see here, several brain targets have been used for stimulation, but it also has shown some mixed results and a high variability in terms of efficacy in randomized clinical trials. So basically, it didn't reach the clinical endpoints. But recent studies suggest that the reason that this focal open loop stimulation failed to reliably treat the psychiatric symptoms is partially due to a target engagement failure, given that many of these psychiatric disorders or psychiatric symptoms actually arise from communication failure between distributed brain networks and not necessarily from a single brain region. So we've been recently working on a project funded by the US National Institute of Mental Health and in collaboration with Dr. Alec Veach from the Psychiatry Department of UMN. And our goal here is to design an implantable microchip that could implement a new mechanism to correct this interregional communication for treating mood and also anxiety disorders. So my PhD student, Yusuf Shin, has been working on this project. So we have implemented, for example, features or measures of synchrony or connectivity between multiple regions of the brain with very efficient hardware that is possible to scale up to many channels on the chip, which is an ongoing work. And there are also many challenges that we believe state-of-the-art machine learning techniques could be essential in order to address those, in order to better optimize stimulation strategies for mental disorders. And this is another related application for predicting mental fatigue in non-human primates that are performing a cognitively demanding task. So mental fatigue is actually a very common symptom of mental disorders and also traumatic brain injury. So here we explore the possibility of using machine learning to predict the periods of mental fatigue in order to control deep brain stimulation in the central thalamus to restore the cognitive function. So in this particular work, we focus on the decoding, but the end goal of the system is implementing a closed loop system. So we use multiple ECOG channels or multi-region cortical recordings, and we were able to decode these episodes of mental fatigue. And this is in collaboration with Nicholas Schiff's group from Cornell Weill, who is a pioneer in deep brain stimulation for traumatic brain injury. So we're currently working on exploring other machine learning tools to better optimize this closed loop system for this application and also for other neurological disorders. So overall, my message here is that there's a great potential for using advanced signal processing and machine learning techniques in order to design a smarter and more effective neural interfaces for a wide range of neurological disorders. So with that, I would like to acknowledge my current team, my students at EPFL, and also my former lab at Cornell, and our collaborators, and also funding sources. And thank you for your attention. I'm happy to take some questions.
Well, thank you very much, Mahsa. That was a great talk. You know, it was a bit, it was a bit, you know,
yeah,
biased for me because
okay.
you know, I love the field, so I'm a bit biased about it. I just want to open the floor for any questions. You can unmute your mic and go ahead. Greg Watkins.
Yeah, thanks, Ahmed. Mahsa, really interesting talk. You talked about two conflicting requirements or ideas there. One, that you had an infinitely large number of sensors, and the other that you had an infinitely small chip. So if I take it to the limits, do you have a feeling for what the practical state of the art is in terms of balancing chip area with sensors, considering just the reality of a chip that you need to have a feed through, you need to have cables to the sensors and so on?
Right. Yeah. And as I mentioned, so recently there's been a lot of interest in reducing the area while power, so pushing down the power to microwatt, even sub-microwatt per channel had been achieved in maybe 5 years ago, I would say. But now trying to also reduce the area so that we could have thousands of channels on the chip is quite challenging. So as far as I know, I think this design, which is doing a multiplexing, dealing with many challenges to cancel the DC offset from inputs that are actually being switched between multiple electrodes, and at the same time achieving high dynamic range. So this design is doing a very good job in terms of pushing down both power consumption and area. Noise, input referred noise is a bit, I think, at a higher end for this design, but I would say these numbers are at the moment really close to state of the art. But on the other hand, really, in my opinion, when we are thinking of doing, for example, machine learning on the chip, there might be also some flexibility in terms of, the non-idealities of the front end. So we may not really need to design ultra low noise circuits. So there's some tolerance in terms of the machine learning algorithms to non-idealities in the circuit. So I think it is important to look at the system as a whole and try to really achieve the right balance in terms of, different components that are on the chip, not just, going for extremely low power and area, and that, on the other hand, maybe sometimes affecting other performance metrics that could be quite important.
Okay, thank you.
Thanks for the question.
Yep. Next question. Anyone? If not, maybe I ask one question regarding the tremor detection. For that tremor detection, how long was the data that's used?
Yeah, the data was quite short. As you can imagine, it is recorded with externalized cables during DBS surgery.
Yeah.
The maximum duration of this data is like 10 minutes.
10 minutes. Okay.
Yes, for each patient.
Yeah. And I think like going back to what Greg Watkins asked, so the patient acceptance of surgery, for example, in epilepsy, it's or these techniques or the implant, let's say NeuroPace or other things, it plays a major role. So what was your experience working with patients or working with these technologies in terms of how is the patient acceptance for any invasive techniques or heavily invasive techniques with respect to the benefits they get?
Exactly. So that's a very important point, and I believe it is really depends on the level of severity of disease and how much patients could benefit from a device that, while knowing that it will have some complications, there will be some surgical complications. Maybe later there would be some bleeding and many other issues that could happen. But even though they know about that, they are willing to have this implant because, for example, patients with seizures that are completely, so they don't respond to any medications. So I think for chronic disorders that are really in severe condition, there is demand for patients. And for the example of mental disorders, from my collaboration with a psychiatrist who is actually in their clinic, they have patients who are, constantly ask about a device that could actually help patients, even though they know that it will be invasive. And so it's, when there's no therapeutic option available, I think this, as long as there's a reasonable level of complications with these devices, which of course there's a lot of control in terms of getting FDA approval to be able to implant this in the patients. I think still there's a lot of demand from patients. But on the other hand, for us as circuit designers, I think there's a lot of opportunity to really improve the complexity, the size of these systems that really don't need to be such bulky and huge, while they are not doing any complex computations on the device. So when you look at the numbers, look at what is being done on each of these devices, this is what we've been doing very carefully. We can see that they're very simple algorithms for a few channels. Usually it is just single channel. So they select one of these 4 channels and then implement very simple algorithms, but it is done with discrete components. It is not done in an energy efficient way. And that is the reason that is increasing the complexity. So this is what we're trying to avoid in the case of the device that we hope to be able to build for mental disorders. So we are targeting very tiny size and also power consumption so that we can reduce the size of battery and minimize the complications.
Fantastic. I have more questions, but I think, Greg, do you have?
Oh, Greg.
Yeah. Oh, sorry, which one?
Go ahead, Greg.
Greg's running, I think.
Oh, you go ahead, Greg. You already started.
Okay, apologies. That was just the boss I talked over, Mahsa, so that's not a good thing from me. So, Mahsa, related to Omit's question a little bit, I think. So you talk about the algorithms and the simplicity or the complexity of the algorithms. So again, you have competing design ideas. On the one hand, you want intelligence close to the sensor, so you can have short control loop times. On the other hand, you want the simplest device possible so that when it goes wrong algorithmically, or when you need to update it, well, you don't need to update it. Have you looked at, or what are your thoughts, in fact, on the feasibility of having a device similar to what you've described that could be remotely upgraded, so you could have evolving algorithms or bug correction or whatever?
Exactly. I think that is the future, and relying on a device that is only, it doesn't update itself, and there's no way to, just with fixed parameters. I don't think that is ideal. So this is actually one direction we are currently pursuing. So we're interested in implementing online learning algorithms that could receive feedback from patients or maybe from physicians from time to time, and also evolve and update the parameters of the model on chip without even feedback. So you could do this in an unsupervised manner. So I think that is definitely the future. And so there are some challenges in terms of implementing such algorithms on the chip, which are more complex than just implementing a offline trained model. But definitely that's extremely important. And when we look at the performance of these algorithms in long term. So for example, if we look at performance of seizure detection algorithm in maybe several days of recording, the performance significantly drops if you don't update these parameters. And I think this is what happens for a device like RNS, and the patients need to go back to clinic to update the parameters. That's a great question.
Okay, thanks very much.
Thank you.
Thanks, Ronnie.
Okay, it's a little bit of an expansion of the first question that Greg Watkins asked, and forgive me if it's not really your field, but I'm curious about the longevity of these devices. If you make them really small, and then someone like me comes along and says, "Well, you need this gigantic package to put it in," and it makes it impractical, or if it's battery powered, as you said, with a deep brain stimulators, it has to be replaced every once in a while. So what is the sort of leading edge, or what is it that you're looking at as far as the longevity of these chips, and how are you able to implant them for a long period of time? What are the safeguards?
Yeah, that's also a great question. I think for devices that are currently, battery powered devices with relatively high power consumption, as they're open loop like DBS, with large batteries. So they need battery replacement every maybe 3 to 5 years. So on one hand, we want to reduce the size of battery, and we want to reduce the power consumption. So for example, for a device with like DBS, I think there's, I would say the cutting edge research is trying to move toward a cranial implant rather than having a chest implanted device, which has, you know, complications with noise and the extension leads. And going for a cranial implant, obviously you will have a smaller, you know, space for putting a battery. So again, designing for low power is important. But I think the goal should be to go beyond that 3 to 5 years of, you know, battery replacement that we have for current devices, which as we move toward closed loop, I think the power consumption is going to significantly decrease, especially as we don't need to do wireless transmission. So wireless transmission is also the major, you know, reason for draining the battery of a device like RNS or for example, the Medtronics device, because they rely on external you know, processing, because they have very limited, you know, channel count and processing on the device. So I think that all of these, you know, should be basically target for improving, not just reducing the size. But as you know, like companies like Neuralink also are pushing to really going for very tiny cranial implants, something that you could implant through a bar hole, maybe. In the skull, and then you need to rely on wireless power and basically a lot of complications on that front to be addressed. But definitely longevity is going to be a very, very important factor for the next generation of these devices.
Thank you.
Okay, so we have one question in the chat. It's Brown is asking, the closed loop DBS for mental disorder, what is the control input signal from DBS electrodes or other signals, EEG or ECOG?
So it could be either ECOG or local field potential. So it, we look at both cortical signals and deep brain LFP. And what is important is the coupling between the two. So there are different ways to look at or to measure this synchrony between brain regions, but usually, so one way we are following is a method that we are basically applying a phase lock to stimulation in a way that we stimulate at particular phases of a cortical signal in a deep brain region. But there are also ways to look at, again, like for example, phase amplitude coupling or phase locking value between an ECOG signal and a deep brain LFP signal.
Okay. Fantastic, thanks Mahsa, thanks. You know, I said I'm biased and slides like this with hundreds of micrometer by hundreds of micrometer full of digital processing and circuits makes me very excited and I'm sure there are a lot for our colleagues, anyone with real-time, on-the-fly, online need of feature extraction, decision-making, and the title of the talk says it all, smart, like a smart implant. If you are sending the data outside and you can do, you know, you can do the processing on a GPU and come back the next morning, perhaps that's not the field that you need. But if you really need a real-time decision making, like for example, preventing a seizure or correcting movement, it is a great opportunity to contact Mahsa and perhaps start a collaboration. I know I'm going to do that, and I encourage this. Yep. Okay. Thank you very much, all, and thanks everyone for attending. Thanks, Mahsa.
Thank you.
Yep.
Thank you, Mahsa.
Bye bye.
Thank you. Bye bye.
Bye bye.